So today we're going to be talking about a few things. First, we're going to explain while writing down the energy balance for a flow system. Then we're going to derive and explain the terms in the Bernoulli equation as it arises in part B1. Then we're going to use B1 to calculate the temperature increase of water arising from flow at constant velocity and potential energy with a drop of 900,000 pascals. And finally, we're going to use B2 to calculate the velocity of air arising from a pressure drop of 10,000 pascals. So for this first part here, what I'm going to do is I'm going to go ahead and draw out this flow system that we're working with here. So we're going to have some system and we're going to have some inflow of mass, some outflow of mass, where we can have some initial volume and initial pressure. So this is going to be P and V in. And we're going to have a pressure out and a volume out. So now we can kind of go ahead and define our system here. So we say that there is some amount of material flowing in, some amount of material flowing out. We have some amount of material in our system. And so we can go ahead, we can try and write an energy balance for this, right? So if we look at all the components here, we're going to have some mass, some potential energy, some kinetic energy, and some gravitational potential energy. It's G here. And what we end up doing is we want to focus on a differential amount of change here. So if we really wanted to go ahead and balance this out all the way, we can go ahead and we could do the same thing, basically. So our potential energy plus our kinetic energy plus our gravitational potential energy out times the differential amount of mass, or actually not out, we're going to focus on the in, where you want to go in minus out. In, differential amount of mass in, and then we would subtract the same components from the out source, differential amount of mass out. And if we look back at our system here, we could do a couple things to it. We could go ahead and we can add a heat source. So here we are, we're going to add heat that's maybe on a like some open flame or an electrical heater, something like that. So what we're going to do is we're going to add a heat component to this. So differential amount of heat. And there is also work being done on the system, so we also take that into account. And what we have here now is an energy balance for this flow system. So now let's go ahead, let's take a look at this component here, our work component. Now, when we talk about work as it applies to this system we have here, we are looking at this component here where we have some amount of mass going in. However, to be injected into the system, there needs to be some sort of pressure behind it, and this pressure is going to be spread over that volume. So if we were really to look at this inlet here, we have an expression that looks something a little bit like this pressure in multiplied by the differential volume at the inlet. Now, we know something about this component here. This component is related to the mass by the density equation. And so we have the mass in is equal to density times volume in, right? So we could go ahead, we take the differential for each of these. Our density is a constant, so we don't focus on the differential for that. And we end up with an expression for this dV in terms of the differential amount of mass. So if we were really to re-express this, then we would have the pressure at the inlet times the differential amount of mass in, so dm in, over the density. And this is how we describe our differential work. So when we look at this work equation that we just defined, since we are talking about a system and we are injecting mass into that system, we go ahead and we can call this the injection mass. This is the work that's being done on the system by injecting mass into the system. However, we also see that there is an outlet for our flow system here. We have something going in, and this system is pushing out some of the mass that we are putting in. And so when we want to go ahead and simplify that into an equation, it looks very similar to this equation. It's just going to be the same P out this time, because we're looking at the pressure at the outlet, times the mass, the differential amount of mass going out over the density of the material going out. So I'm going to put in it here as well. And this is going to be our ejection work. And this work is going to be negative because when we look at work in this case scenario, we're looking at the fact that the system that we are creating we're looking at it from the outside in. We're looking at the fact that we are doing work to the system. So if we're looking at it to that standpoint, to get the work done to the system, we need to subtract the work done by the system. So let me go down here, and I'm just going to rewrite this out. I'm going to copy this out because I don't want to rewrite that. And we're going to copy that, and we'll paste that right here. Yeah, so we're going to mark that off. So we still have our differential amount of heat, dq. And now we're going to add our injection work, which I'm going to write it a bit differently. I'm going to rewrite it as the pressure in over the density in. Don't get confused between those two. This is rho, this is pressure, times the differential amount of mass in minus the pressure at the outlet over the density at the outlet times the differential amount of mass at the outlet. So now let's go back to our system over here. So we've talked about the fact that we have some flow work going in, we have some flow work going out, we have our injection and ejection work. And this in its total is called the flow work of this system. This is the work that is happening just by pure flow in and out. However, there are other ways we can apply work to a system. Say if this was a system with gas in it, we could go ahead, we can put an airtight piston on the top, and we could compress the gas, and that would be considered doing work to the system. Over here, since this is flow in, flow out, we are dealing with a liquid of some sort. So we can go ahead and we can add maybe a stirrer to it. And this stirrer, what it's going to end up doing, it's going to provide us another source of work known as the non-flow work. So this is also something we could take into account with our equation here. So we have this big long thing and then our non-flow work. So from here, we see that we have dm in, dm out, dm in, dm out. So we could go ahead, combine that in. So if we rewrite this, let's see, just there for now. We have our d e squared over 2 plus potential equal to the potential plus This is our dmin component. We're going to have our P over density plus kinetic energy over 2 plus gravitational energy in times our differential amount of mass in plus, or rather minus, our potential plus P over rho plus V squared over 2 plus gravitational out times differential amount of mass out plus our differential amount of work, our heat, plus our non-flow work. So the next simplification we can do within our process here, we can look at this part here. And we can redefine this part using this equation here, where we have H is equal to potential energy plus PV, where this V is known as the specific volume. Specific volume. Now, we can also go ahead and rewrite this as the potential energy plus P over the density, which is this rho right here. And we can do this because this specific volume, its units are in, say if we had everything here in moles, this thing would be in some measurement like meters cubed over mole. Well, this seems awfully familiar to density. In fact, this is just the density's inverse. It's the reciprocal of the density. Since we have some mass unit down here, and we have some measurement or some volume on the top. So mass over volume, that is our density. Volume over mass, we have the inverse of our density. So we can go ahead and rewrite this H as the potential plus the pressure over the density. And when we go ahead and we do that, the simplification becomes something a little bit like this, where we have dm v squared over, I don't know where z got there from, v squared over 2 gz equals, now we can go ahead, we can replace this by h. So this is going to be h plus v squared over 2 plus gz in differential mass in minus the, same thing here, we got our h, so h plus v squared over 2 plus gz out differential mass out. Okay. Woo. Pen's not working. Okay, I think it's working again. M out. And up here, we have our differential heat, and this should be our differential non-flow work, plus our differential non-flow work. So this is our B1. This is the equation we're going to use to go ahead and describe a flow system. So now the next thing we want to do here, let's just scroll back up. We've already written down the energy balance for our flow system. Now let's go ahead, let's use this energy balance to go ahead and derive the Bernoulli equation. So before we start, let's go ahead, we'll define a new system just right down here. Oh, I still want this in view. So let's use this color. So let's go ahead, let's assume a new system. Let's assume that we have some sort of pipe. Well, you know, if I could draw lines, that'd be nice. Sure, better. We have this pipe here. And let's say this pipe is just, it's just like 10 meters long or something like that. Now, what we have here is we have some mass flowing in, we have some mass flowing out. It's a straight pipe. So there is this constant stream of mass going in and out. And so let's assume steady state conditions. Steady state conditions. So when we assume a steady state, we need to go ahead, we need to assume two things. So first thing we want to assume is that there is no more change. There's no change with time. So no time dependent change. So with respect to our energy balance here, this is for our system. And all of this, that's just going to be zero. There's no change within our system. Everything that goes in goes out. And so there's not going to be an accumulation with respect to time. And so conversely, the second thing that we want to go ahead and assume is there is no change in mass. No change in mass. So we can use the relationship that the differential amount of mass in is equal to the differential amount of mass out, which we could just represent as this differential amount of mass. So having these two assumptions in place, we can go ahead and start deriving Bernoulli's equation. So now that we have all that talk done about steady state, what that means for this case, let's go ahead and set up this equation. So we're going to set that left side equal to 0. Remember, there's no time-dependent change right now. And so on this side, we're going to have the potential at side 2 minus the potential at side 1 plus the pressure at 1 plus the pressure at 2. We're assuming a uniform density here, so we're just going to go over one row. This is minus P2 minus P1. P2 minus P1. And then we're going to add the difference in the gravitational potential energies. And lastly, we're going to have the difference V out squared minus V in squared over 2. And of course, differential amount of heat plus the differential amount of non-flow work. Okay, and from now here, I'm just going to use numbers here for continuity purpose. Come on. V2, V1. So now what we want to do here, let's see, we're going to, remember, differential mass. We'll go ahead, we're going to take these terms. We'll move them to this side. And then we're going to rewrite this. Remember to reverse our numerators here. So P1 minus P2 over rho plus G times Z1 minus Z2 plus V1 squared minus V2 squared over 2 multiplied by dm. And this is going to be equal to our potential energy here, our internal energy, U2 minus U1 differential mass plus differential heat plus differential non-flow work. And we can make a couple simplifications here, most notably, we can go ahead, we can cancel out these differential mass things we have here and put these over differential mass. And now what we have here is we have P1 minus P2 over P plus G, weird G, GZ1 minus Z2 plus V1 squared minus V2 squared over 2 is equal to U2 minus U1 plus dq over m dm plus d non-flow work over dm. So what we have now on this side here, this is something that we call the frictional heating. Frictional heating. And it's pretty self-explanatory. It's the heat that occurs within a system due to friction. As we all know, friction creates heat, and this accounts for the difference in heat due to that friction. And what we're going to do, we're just going to go ahead and assume that this is approximately equal to 0. Our non-flow work also approximately equal to 0. Very little. We can make it negligible. And so let's rewrite this one more final time. Come on. Computer's messing with me a lot today. So finally, what we have is P1 minus P2 over rho plus GZ1 minus Z2 plus V1 squared minus V2 squared over 2 equals 0. And this, ladies and gentlemen, is Bernoulli's equation. And so that's part B2 done, nice and ready for us. So now we're just going to jump ahead here a bit. This is actually, we're going to solve for B4 before we go and solve for B3, just because we have now learned Bernoulli's principle and we can apply it to this type of problem. So here we have a system. We have defined the fact that its internal pressure is 10 to the 4th pascals, where now there is a hole here, and it is going to experience a pressure drop all the way down to 0 pascals. The density of air is about 1.2 kilograms per meter cubed. Our initial velocity is 0. We're going to find the final velocity at this open point here. So first things first, let's go ahead. Let's go rewrite Bernoulli's equation. So we just derived that. So P1 minus P2 over density air and plus V1 squared minus V2 squared over 2. And we're going to assume there's no height change, so we're just not going to focus on that gravitational potential energy part. So we're just going to go equal to 0. Just double check that, make sure it's right. Yep, looks good. So let's go ahead, let's solve for V2 here. So first things first, we're going to move this over to this side. And to do that, we're just going to flip around the top part. So V1 squared minus V2 squared over 2 is equal to P2 minus P1 over density air. And then the next thing we want to do, we want to multiply all that by 2. So V1 squared minus V2 squared equals 2 P2 minus P1 over density air. Then what we're going to do, we're going to subtract V1 here. V1 squared actually. Whoa, hi. Go away. Actually, to make this easier on ourselves, let's go ahead and just try and plug in some values here, just to make things a tad bit easier. So V1, so this is going to be 0. don't need to worry about that. Our pressure 2 is going to be 0, so we shouldn't worry about that either. And so now we're going to plug in 1.2 here. So negative V2 squared is equal to negative 2 times pressure 1 over 1.2. These negatives are going to cancel each other out. And then we're going to square root both sides. So we should get V2 is equal to the square root of 2 times pressure 1 over 1.2. And this we can now very easily calculate. We know our initial pressure, that's 10 to the 4th pascals. And we know our density of air, that's 1.2. Oh, whoopsie. And that's pretty much all we need to solve this problem. My pen is deciding to not work again. Let's see if this solves it. Yep. So now what we can do, we're just going to plug in some values. Equals square root of 2 times 10 to the 4th over 1.2. And I have my handy dandy TI-84 right here. And what we're going to do, we're just going to type this in and see what it gives us. So it's the square root of 2 times 10 to the 4th, 10 to the 4th, all over, well, let's do it this way. 10 to the 4th, and then the square root of 1.2, that divided by that. And it is giving me a velocity of 129 point, about, we're going to call that 10. And the units for this is, remember, we have pascals up here. We have kilograms per meters cubed up here. We are square rooting that. So the velocity here is going to be meters per second, I believe. I can double check that. So yes, after canceling out all the units, we do find our final velocity to be 129-ish meters per second. So now for this last part, B3, we're going to use the energy balance that we derived in the first part of this video to calculate the temperature increase of water arising from flow at a constant velocity and potential energy with a pressure drop of 900,000 pascals. So first things first, I have gone out and rewritten that energy balance that in question. And what I'm going to do is I'm going to rewrite, pardon me, thought I was going to sneeze, didn't happen. We can go ahead and assume that we have, some steady state. That was about as curvy as it gets. I don't know what that was. So we have, let's say, some steady state, something like a steel bar here, where our velocity going in is equal to our velocity coming out. There is no change in potential energy, so we can ignore all of those things. So let's go ahead and say that going in, there is a pressure in, a pressure out, and the velocities are same, is constant, and our gravitational potential energy is also constant. Now, we can do a couple things with this information that we have. So, since we have a constant velocity and a constant gravitational potential energy, we're going to assume that this is a steady state. It's a steady state reaction or steady state flow. So, what that tells us is that this side is going to be 0. There's no time-dependent change here. We are ignoring velocity and our gravity. As before, our differential mass in is equal to our differential mass out, which is just going to be equal to a singular differential mass. We are not adding any heat, and there is no non-flow work, there's no stirrer, there's no heater. So, in the end, what we are left with is 0 is equal to the difference H in minus H out times the differential amount of mass in the system. So from this point onwards, we can divide on both sides by the differential mass. So what we're left with is the enthalpy in is equal to the enthalpy out. And enthalpy can be rewritten as the potential or the internal energy plus the pressure over the density. And we could do this for both sides. And essentially, since we have a steady state reaction here, and especially we have an incompressible flow, or incompressible flow, this means that the density does not change. So our P in is equal to our P out. And the pressure, or I mean, sorry, not the pressure, the density over here in question is of water, which we know to be 1,000 kilograms per meter cubed. So using that, we can go ahead, we can try and get our internal energies on one side. So if we, that's not what I wanted to do. We can go ahead, we can try and do that. So what we have here now is, so our internal energy in minus our internal energy out is equal to our pressure out minus our pressure in over the density of H2O. And we can go ahead, rewrite our left side as the specific heat of water times the change in temperature. Now, the specific heat of water in joules per grams Kelvin is 4.184. However, grams isn't going to cut it because we are working with kilograms here. So plugging that in, we want to make sure that our variables stay, our units stay constant, consistent. So this is going to be equal to 1,480, let's just go 80 joules per kilogram Kelvin. So now we can go ahead, we can plug in our values. So 4,180 joules per kilogram Kelvin times, I'm just going to rename this as delta T, is equal to, remember our pressure out, we are undergoing a pressure drop of 9 times 10 to the 5th pascals. So our pressure out is going to be 0 here. Let's see. I'm actually going to go ahead and reverse one thing. We're going to make our pressure out, our internal energy out, internal energy in. Pressure in minus pressure out. I'm just redoing the way I do this subtraction here to make it consistent because I had made that mistake right here. So our pressure out so our pressure, no, other way around. Now my mouse isn't showing up. Okay, hopefully this is working now. Pressure in. This is our pressure out. Pressure in. Pressure out. So, just double check. Pressure out. Out minus in here, in minus out there. Yep. So our pressure in is 9 times 10 to the 5th pascals minus 0 pascals. That is what is at our outlet. We're going to that pressure drop. All over 1,000 kilograms per meter cubed. Now, all these units are going to cancel out. It should give us units in Kelvin here. So I'm just going to go ahead. I'm going to solve for delta T here. If I go into my TI-84 once more. So we have 9 times 10 times 10 to the 5th pascals divided by 1,000 kilograms per meters cubed. And we're going to divide by 4,180 joules per kilogram Kelvin. And that gives our delta T as 0.215 Kelvin. And that solves B3 for us.